we deployed our microservices application and it's running just fine inside the Kubernetes cluster. However, there are several things our configuration files for the microservices are missing. It's missing several best practices of Kubernetes configuration. So basically, even though the microservices application is running fine and we don't have any problems, we actually created the Kubernetes YAML files with several bad practices. So in this lecture, we're going to learn different Kubernetes best practices, and we will improve our configuration files for all our microservices using these best practices one by one. The first best practice in Kubernetes configuration files is that we need to define specific image versions for every image that we use inside our pods. In our case, because the microservice applications needed a specific version tag in order to work, we have already implemented this into our project. But it is not always the case, so it is important to understand this as the best practice. And the reason for that is whenever we don't specify a specific version tag, Kubernetes automatically pulls the latest version of that image. And that means whenever the new image gets built and pushed to the repository and the pod gets restarted, it will eventually pull the latest image and start with the latest image version, which makes it unpredictable and impossible to know exactly what versions you have running in your cluster. So fixating the image version basically always gives you the control and visibility of what versions of applications are currently running inside the cluster. So as you can see in our project, we specified this version here, which is defined after the image name. For this Google project, you can actually check the release notes to understand exactly what version to use. In other projects, we can ask developers themselves, or if we are the ones basically controlling and handling the CI/CD pipeline for the application and building the image, we will know ourselves exactly what image versions we're building. So in this case, we have the same versioning for all the microservices. So basically, everyone has the same version schema and the same versioning. So now we have versioned all our microservice images, which means one best practice has already been implemented. The next best practice that we're going to define in our Kubernetes configuration file is liveness probe. Generally, we know that Kubernetes has an intelligent way of managing all of its resources. Like it knows the pod status, so when the pod dies, it automatically restarts. So we don't need to worry about that. But what about when the application inside the pod dies, like the container that is running inside the pod? So the pod is still running, so Kubernetes thinks that everything is fine here, nothing to do, but in reality that application is not accessible because the container inside the pod crashed or maybe stuck in a loop because of a bug, so it can't accept any traffic. How do we let Kubernetes know in this case whether the application inside the pod is running successfully or maybe it crashed or has some issue, even if the pod itself is running and in a healthy state, so that Kubernetes automatically restarts the application in it? Well, we tell Kubernetes exactly that information using liveness probe. With liveness probe defined, Kubernetes will automatically restart the pod when the application is crashing or is having an issue. So how do we define a liveness probe in our container? It's actually a very simple script or a tiny program that just pings the application endpoint every 5 seconds or 10 seconds to check that the application responds, so it's running successfully. And we can actually add this simple script or command ourselves in the configuration, but in our case, the developers tell us that in every image, they actually added a small application, a small program that can be executed to check whether the application in pod is accessible and healthy. So we can use that in the liveness probe. So let's see how that looks like in the configuration. So liveness probe is a container attribute So we're going to define it inside this container configuration on the same level as name, image, etc. And the attribute is called liveness probe. Here we define the attribute depending on what protocol the application uses to return the health check information. This could be HTTP or TCP. In this case, however, these specific microservice applications are using a gRPC protocol, which is a more modern communication framework basically for applications. So we will define gRPC right here. And it is one of the attributes that liveness probe actually supports. Once we define the protocol, we also need to tell the liveness probe what port it should send that gRPC request to. This microservice runs and responds to requests on port 8080, so that's what we will define here. Next, we need to define how often or how regularly the endpoint of the application should be checked for its health. So we define the period seconds. So we say every 5 seconds, please check that the application is fine. So this will do the actual health check of the application. And this will define how often this application health check will run. So every 5 seconds, we have the application health state. And that's how we define the liveness probe. Since in our case, we want to complete this check on every single microservice, you can basically just copy this code and configure that in every other microservice application. And of course, you will need to adjust the port number for the respective microservice. So you can go ahead and copy and paste that in every single microservice configuration. Another best practice is defining what's called a readiness probe for each container. We said that Kubernetes knows the pod state, but it doesn't know the application state inside the pod. And we solve this problem with a liveness probe, right? But liveness probe helps Kubernetes see that the application is running successfully only after the application actually started. But what about the starting up process itself of the application? So pod was created and now the application inside is actually starting up. How does Kubernetes know that the application is fully initiated and started and ready to receive the requests? That's where readiness probe helps. It lets Kubernetes know that the application is ready to receive traffic. And this is important because if your application needs 2 minutes to start, without a readiness probe, all the requests to it will fail during those 2 minutes and you will have a bunch of errors in your applications. So how do we configure a readiness probe? Actually very similarly to the liveness probe, because they both basically check the application availability. Readiness probe does it during the application startup process, while liveness probe does it while the application is already running. So let's see the configuration syntax for that. On the same level as liveness probe, we have readiness probe with exactly the same attributes as liveness probe. So we have the interval time, 5 seconds, and the execution of this probe. So basically when the pod gets created and the application is starting up inside, every 5 seconds until the application is fully started, this will actually check whether the application is fully initiated or not. And only once fully started, readiness probe will tell Kubernetes the application is ready to receive traffic. And after that, a liveness probe will then check every 5 seconds that the application stays running and healthy after the startup. And the same way, you can just copy this readiness probe section here and basically configure it in all other microservices. And again, adjust the port number. And the final note on readiness and liveness probes is that, as I mentioned, these microservice applications are using gRPC protocol. And that's why we have used gRPC attribute. But other applications may use other protocols. So there are 2 alternatives to this to check the application health state. So the first alternative is using a TCP socket. And we're going to configure that actually for Redis. So let's see how that actually looks like. So I'm going to copy this and go to the Redis card here. This time we're going to define an attribute called TCP socket. And the port on which we want to open that socket, which is the application port, because that's what we are checking. And the same configuration here as well. So basically with this configuration, with the TCP socket, the kubelet will attempt to open a socket to your container on this port where the application is running. If it succeeds to establish a connection on this port, the container is considered to be healthy. So the application is running and is reachable. If it cannot establish that connection, then the application is considered to be failing. So the readiness probe or liveness probe will fail for the application. So that's how it works. Pretty easy and straightforward. And note that generally for readiness and liveness probes, no matter if it's a command execution or TCP socket, we can actually execute initial delay seconds in case we know that application actually takes longer to start, which looks like this. So this basically tells kubelet that it should wait 5 seconds before performing the first liveness probe or the first readiness probe. Again, can be useful for applications that you know take some time to start or basically become ready. So TCP socket is the second option of health checks, and we have the third option, which is checking the application health on HTTP endpoint. So for example, if the application had an endpoint inside the application that exposes basically the health status of the application itself, we could hit that endpoint to check whether application is healthy or not. And for that, the attribute name is HTTP GET. Then we have the path, which is basically the URL of the endpoint, the URL of the health endpoint in the application, and the port number where the application is accessible. So this configuration will tell kubelet there is an HTTP endpoint in the application on this port, and this URL is where you can check whether or not the application is healthy or not. We have already improved our configuration file with some of the best practices, but there are a couple more best practices that we can add to our configuration file. First of all, we need to define for each container something called resource requests. Some applications may need more CPU and memory resources than others. So to make sure that your application container has enough resources when it starts inside the pod, you should define resource requests for each of your containers. And defining that is actually pretty simple. Again, inside the container configuration section, right, on the same level as liveness probe and readiness probe, we define an attribute called resources. And then inside that, we have requests. So these are the requests for CPU and RAM resources. And we actually have some average value for CPU and memory in case your application is just very super normal. It doesn't have any special requirement for CPU or memory resources. We can actually define these average values here. And for CPU, this average resource requirement will be around 100 M, which stands for millicore. And for memory, it could be 64 MI, which stands for megabyte. So this is something that we can define as a resource request for all the containers in our configuration, as long as they don't have any special requirements. And with this defined, your containers will have enough resources to consume. But what if, while the container is running, it actually needs more than what it requested in resources? So what if it goes over limit, so to say? For example, this can happen if one application gets too much data that it needs to load into memory, or the application has a bug inside with some infinite loop and starts consuming all the CPU available on that node. In this case, one single container will actually start consuming more than the requested resources, and it can take all the CPU or memory of that node. So other pods running on the same node will not have enough resources, so they must be rescheduled. Of course, you want to avoid such situations where one container consumes all the resources on the node, and you can do that by setting resource limits for each container in addition to resource requests. So we define the limits inside the resources block for same resources, the CPU and memory. And we can actually give double the amount in both cases, like this. So basically, the CPU and memory resources defined in a request is something that we expect the container to need when it's running in a normal mode. However, if it goes over limit and suddenly starts needing more than what it requested, then we actually set the limit for those resources so it can actually consume up to 200 M CPU or 128 MI memory, but that's the limit, right? It can't go over that amount. And obviously, you can calculate this value and basically see what makes sense depending on how big your node is, for example. So if you have a bigger node, you can give each container more resources, or if it's a super small node, then you can maybe limit your resource consumption per container a little bit more. And remember, if you put values in your limits here, which are larger than your biggest node, your pod will never be scheduled. So as I said, this would be like an average application resource consumption, and you could actually set this on all the microservices. However, as I mentioned, some applications may actually require more resources than others. So for example, in our case, we could ask developers, because they know the microservices much better than we do, we can ask them whether any microservice actually needs more resources than normal or less than normal so that we can adjust these values. And let's say developers tell us that add service, microservice, is more memory and CPU intensive, so we need to increase those values for add service. So in the add service, again, in the container definition, we can paste in the resources values and we can basically increase them. So let's say we give it 2 times the average CPU and increase its limit to 300 M. We also give it more memory request and limit so that add service, microservice actually gets more resources than other services. And finally, Redis will need more memory resources, of course, because it is a memory database, but it will need less CPU resources. So we can adjust that as well. And again, let's take our average resource definition and paste it in here. And as we said, it needs more memory because it's a memory database, so it needs to store more data than other applications. So we give it 200 MI memory, but we set the CPU request and limit to lower values. So this could be our resources configuration for the microservices, where every container in the configuration has this resources section where resource requests and limits are defined. For most of the microservices, we have basically the average values defined like this, and for some applications that need more CPU or memory consumption or less than average, we can adjust those values. Another thing that we need to fix in our configuration file is actually exposing an external service using node port service type. So the problem here is that even though using node port service is super easy, it is actually a bad practice because it exposes cluster to a security risk. Why? Because it opens a port, as we saw, a node port on all worker nodes in the cluster, where it can be directly accessed by external sources. So you have multiple entry points in the cluster and you increase the attack surface. The best practice is to only use internal services and have one entry point to the cluster where all requests come in, and ideally that entry point should be sitting outside the cluster on a separate server. So instead of type node port, we can use a load balancer type, which uses the cloud platform's load balancer to create an external single entry point for the cluster. So load balancer will get all the requests coming from the browser or from other external sources to the application, and this will be the cloud provider's load balancer, and load balancer will then redirect that request to the cluster, to the internal service which is responsible for that request. As an alternative, we can also use ingress controller to direct traffic to the internal services, which you already learned in the previous lectures. In our case, we will change the service type to load balancer, and this will give us a more secure connectivity to our application. And we can actually remove this node port attribute here. And finally, one more thing we need to fix in these configuration files is the number of replicas, which is by default, when we do not provide any value for it, it's 1. So we have one replica for each pod, and that's what we actually saw here, right? We have per microservice just one replica running. And having one replica per application means that if that pod crashes, you have a service downtime until the new pod gets created. By increasing the replica count to 2 or 3 replicas or even more, you basically make sure that even if one of the replicas dies, the application will always remain available to other microservices or to the external requests. And we can very easily avoid that in Kubernetes by just always deploying more than one replica of any application. So as I said, by default, the replicas is 1. So if you do not define replicas attribute at all, this will be the value. But in best practices, we should set it to at least 2 replicas per application. Again, copy and paste this for every other microservice. So you can now deploy your microservices again with the improved configuration file that we adjusted using Kubernetes best practices. Now, apart from the Kubernetes best practices that we use to improve our configuration file, there are a couple of more that I want to mention here. One best practice is to always use more than one worker node for your cluster. This is actually very logical because if you just have one server where all your pods are running, you have a single point of failure. So if something happens to that node, basically all your applications are gone, stopped, and not accessible. So you want to replicate your nodes as well so that you have at least 2 or 3 worker nodes in your cluster. Even if you're running a simple application and if you have a small cluster, and especially if you want to run multiple replicas of your pods, ideally you want each replica to run on a different node and not all the replicas basically running on the same node, because that doesn't give you that much backup if something happens to the node itself. And this could actually happen if the server crashes or someone reboots the server to make updates or clean up some stuff there, and these pods will stop on it. So with multiple nodes, basically, even if the server crashes or one node crashes, all the pods can be rescheduled to another healthy node. Another best practice is using labels in your resources. So basically labeling all your Kubernetes components, which we already did in our configuration files where we labeled our pods. And labels are key value pairs, as we saw here, key and value, that attach to Kubernetes components like pods and services, deployments. And labeling a component is like giving custom identifiers to your components so that you can address them directly or reference them in other Kubernetes resources. The use case that we saw here was using labels to group pods based on the application they belong to and then referencing them in the service component. But as I said, it's a good practice to label other resources, not just pods. Another best practice in Kubernetes is using namespaces to isolate your Kubernetes resources from each other. You already learned about namespaces and you know that logically grouping applications and other components into namespaces makes managing your cluster way easier compared to just throwing all the pods and services and all the components they need in one namespace. And namespace is also very useful not just for grouping certain resources, but also for defining different privileges inside the cluster based on the namespace. So you can have multiple teams basically working on the same cluster, but each one having and managing their own namespace, and they will get the privileges only for that namespace. And we saw a namespace scoped privilege component in one of the previous lectures where we talked about roles and role bindings. And again, in our example, we actually used a namespace. We created a new namespace for the microservices and deployed the microservices there instead of creating them all in the default namespace. And this is actually totally up to the team how they decide to group and separate applications in namespaces. You can actually have one microservice per namespace as well. And there are 3 more security best practices that you need to be aware of when working with Kubernetes. One of them is ensuring that all the images that you're using in your cluster are free of vulnerabilities. This can happen if you're using libraries or tools that have some vulnerabilities for your application inside the container. And you can avoid this by doing vulnerability and security scans on images either manually or in a build pipeline. And the same way you can also scan third-party images that you are basically downloading from public repositories like Docker Hub, for example, to make sure that they don't create any security issues in your cluster. So checking the images for that is actually a best practice. Another security best practice is making sure that you don't have containers running in your cluster that have root access capabilities. This exposes security risk because a container with root access can access more resources and do much more on the host where it's running. And that means if the container has a bug or security issue or someone hacks into it, they can do much more damage to the node, the server where the container is running, with its root privileged access. So having non-root users in the containers will minimize this type of risk. Most of the official images do not use root user. However, if you are using non-official third-party images, it's always a good practice to check whether the container is actually operating in a root user mode. And finally, it is a Kubernetes best practice to update your clusters to the latest Kubernetes version, which is again very logical because in each following version, you have some security issues that were fixed or some bugs that were fixed. So obviously it makes sense to use the latest version with those fixes. And to update the Kubernetes cluster, usually you will need to do it node by node to avoid application downtime or cluster downtime. And that's another reason why it's important to have multiple nodes with multiple pod replicas so that while you're taking down your nodes and upgrading the Kubernetes version on that node, basically you have other nodes and other pod replicas that continue running so that your application doesn't have a downtime.